start then, it is 12 o'clock, by introducing our speaker today, who is working at the Department of Physics at the University of Paderborn in Germany. And he is working in non-Hermitian physics of microcavity polaritons for quite some time, with very interesting works in vortices that we have been following your work for some time. So today he is going to talk about the topic, of course, polariton vortices, creation and control of such topological defect states. So without any further ado, Xuekai, the floor is yours.
Okay, so thank you very much for the introduction and also the invitation. It's a great pleasure to be here to give this talk. Good morning, ladies and gentlemen. My name is Xuekai Ma, and from Paderborn University in Germany. And today I would like to introduce a part of our previous work focusing on the polariton vortices, including the creation and the control dynamics. So first, I'm a theoretician in this work. I also will introduce a bit of the experimental data, but I may not be able to answer the questions related to the experimental details, but the questions are still welcome. Before going, So before going to the scientific part, I would like to briefly introduce our university, Paderborn University. So here is the location of Paderborn. Use laser pointer. So here's Paderborn, and as you can see, it's not that far away from this kind of region, or Hamburg, not to Berlin. It's a little bit to Munich, and to Netherlands, also very easy. I mean, the travel is quite easy to everywhere to the Europe, the other cities. And here's a part of our city, and this is the campus of our university, Paderborn University, and part of city view. Somewhere city center is here. And in our university, there are several research centers we are involved. For example, this collaborative research center tailored nonlinear photonics, supported by DFG, the German Research Foundation, by cooperating with Technical University Dortmund. Dortmund is here, quite close to us. And also we in the Center for Optoelectronics and Photonics, Paderborn. Maybe I cannot see this part. And yeah, it's getting better. And also a part of a newly founded Institute for Photonic Quantum Systems. So here is our group photo. We have a lot of members here, but not all of us work in the field of polariton physics. Here I highlight the polariton group, who's working in the field of nonlinear polariton physics, and here also two other research directions, quantum optics with quantum dot, and also photophysics of organic semiconductors. And I was a postdoc here, and recently I'm promoted to a junior research group leader, but unfortunately we don't have the group photo at the moment. So this is the outline of my talk today. I divided this into 4 parts. The first part, introduction, and third part, and second part and third part with the main part. And I simply in this talk, I divided these 2 kinds of vortices into 2 groups, these vortices. For example, the first one is, I call it non-localized vertices, and I will introduce the formation and manipulation dynamics of such kind of vortices. And generally, these vortices always appear as vortex-antivortex pairs. And the other one is, I call it localized polariton vortices. This localized one always have a ring shape and confined in the middle of the pump. And I will also introduce the creation and the switching dynamics of this kind of vortices, and then conclusion part. So now introduction, I will briefly go through this introduction. I think you are experts in this field, already know what's external polaritons. So an external polariton, so we know in a semiconductor microcavity, an electron could be excited from the valence band to the conduction band, forming an exciton, and the near resonant photon can strongly couple with this exciton, forming a new quasi-particle state. It's known an external polariton. But strong coupling is very hard to be achieved in a bulk medium. Then this strong coupling could be achieved in a planar semiconductor microcavity. So here's the quantum wire in the microcavity, which contains the excitons and with only the in-plane motion. So in this case, the excitons could strongly couple with cavity photons, which perpendicularly propagate. And due to the strong coupling, we can see the normal mode splitting here. For example, this dashed parabola is the cavity photon mode, and the dashed straight line is the quantum wire exciton mode. Due to strong coupling, we can see the normal mode splitting at this position, and then two Polariton branches are formed, the upper Polariton branch and the lower Polariton branch. So I also would like to introduce some very typical properties of Polaritons, why our system are interesting and very rich physical phenomena. So first, they have small effective mass, is around 10,000 times smaller than the free electron mass, and also long coherence with lifetime around roughly from 1 to 100 picoseconds. Which depends on the quality of the microcavity, and they are bosonic quasiparticles. So in this case, we can see the condensation of Polaritons, and they are strong and show strong nonlinearity. So we can study the nonlinear phenomena in this system as well. Polaritons is very interesting because it can be excited both resonantly and non-resonantly. Resonant excitation means we have the pump frequency close to the Polariton resonance, close to this region. So non-resonant excitation, we mean the pump has the energy far above the exciton resonance. For example, here, have a higher energy, then this pump could excite all the particles or carriers to the higher energy state and then relax really fast to the lower Polariton branch here, so by phonon emission. And in this region, Polariton-Polariton interaction will force one go to the highest energy state with high K and one going to the lower energy state, close to K0. So in this case, when the pump intensity is above the threshold, we can see the macroscopic occupation of the Polaritons at the ground state. So here, K0. And here is observation of Polariton condensation. Below the threshold, we can see the parabola when the pump reaches the threshold, we can see the condensation happens here. And what's important is as pump intensity increase further, we can see the energy blue shift if we compare these two, confirming the strong linearity, repulsive one. So the dynamics of Polaritons could be described by, and another excitation could be described by this Gross-Pitaevsky equation. It's also known as nonlinear Schrödinger equation in nonlinear optics, the quite similar form. So if we have looked at this equation, so the dynamics of the Polariton condensates could be described by these terms. So this is dispersion or kinetic energy. If we consider the condensate close to the bottom of the lower Polariton branch, here's the parabola, the dispersion, and then this is the loss rate and nonlinearity. So we first jump this term and come to here. This is a potential part. It's quite similar with the Schrödinger equation. And this E is resonant excitation, means if we have a laser here, then we can excite not resonantly the Polaritons. And what's important in our system is this part, this N is the reservoir density. This reservoir density is can be described, the dynamics of the reservoir density could be described by the second equation. If we have resonant, non-resonant pump here, and this pump will excite the reservoir, and then some reservoir will decay, and some reservoir will, excitant from the reservoir will compensate the condensates. And on the one hand, if we have look at this term, this reservoir will provide the gain, which compensates the loss in this system. On the other hand, GR times N, so behaves like a potential part term in this equation. That's why we call it optically induced potential or reservoir potential to distinguish this one. Normally we can call it external potential or fabricated potential. So in our work, we just simply change this excitation pump by different excitation manners, and then change this external reservoir to check the dynamics of Polariton condensates. This is in scalar model. If we consider the spinor model, so the polarization or the pseudo spin of Polaritons, we could also have this kind of wave function, consider the spin polarization. In some cases, if we have TTM splitting in our system, we could also plus another term like the spin orbital interaction term. So we are really interested in the vortices. So a vortex is defined as a region in a fluid in which the fluid rotates around an X line with a spiraling or circle motion. So here are some spiraling vortices in the nature. For example, the galaxy vortex, like a black hole in the middle, or the wind vortex, like typhoon shape, or the water vortices. The vortices could be also created artificially. For example, the smoke vortices, a smoke vortex, or an optical vortex. So in the lab, it's quite easy to realize this optical vortex. For example, we have fundamental mode here. Then we put a phase modulator in front of this beam. We can generate the phase singularity, and the phase distribution in this way, either clockwise rotation or counter-clockwise rotation. And these two will correspond to the topological charge of the vortices. For example, +1 or -1, depending on the circulating direction of the particles. So this part is quite important because its binary information, plus or minus, is very useful for example, information processing or data storage because of this binary nature of this information, phase information. So that's why these vortices are widely studied in condensates, for example, in atomic condensates, how to create such kind of vortices. At the beginning, we have the condensate here. Then people could use a laser to steer the condensate and then create angular momentum here, orbital angular momentum here, then generate a vortex. If people steer faster and faster, one can say the 2 vortices, 3 vortices, or even 4 vortices could be created. This is in atomic condensates. In Polariton condensates, it's a little bit different because if we have look at this pump profile excitation minor, we have such kind of pump, and in the pump we can say some density minimum or intensity defect, and this intensity defect will give this information to the reservoir. If you still remember this equation, this non-resonant pump will transfer the shape, not phase or something, but the shape to the reservoir, and this reservoir will act as a potential part. Then this potential could trap the condensate in the density minimum, forming a vortex shape. And this is a idea how to create vortices in Polariton condensates. Following this idea, we just try to modulate our pumps to excite different types of vortices. For example, the non-localized vortices, we're starting from the simplest one. This one means we have homogeneous excitation. If our pump is homogeneous and we just put this pump on the sample, we can create some vortices in general. This is because of the initial phase defect of the nonlinear or non-equilibrium nature of polaritons during the condensation. So we always create some vortices in the calculation, but this is a numerical calculation. So we always create some vortices, and these vortices and anti-vortices, they also have interaction, which means in this window, as time evolves, the vortices are not spatially pinned. They are moving all the time due to the interaction. So later, if we're thinking about this pump, so we use 2 same pump, but with different incident angles. For example, they are opposite. Then we can create such kind of a modulated pump distribution. But if we have 4, the other 2 in y direction, then we can create an optical lattice. And this lattice, of course, will first create the similar distribution of the condensate. If we have a look at the background, it's also the lattice shape. And in this case, the lattices could confine the vortices in the spatialized lattice set. For example, here, here, here. But this lattice set is really random because we're starting always from noise in the experiments, always some fluctuation is not controllable. So then we find a method to control this vortices because we would like to manipulate to like the vortices could be used for some, for example, information in the application also. So if, for example, if we have a coherent pulse, very short pulse to launch at this lattice set, one lattice set above this vortices, and this coherent pulse will open a density minimum or create a density minimum of the condensate here. Then the confinement from the upper position of these vortices will become weaker. Then these vortices will be released. then come to the upper lattice side. So by using, then you can see the next step, this vortices already shifted to here. If we land the pause here, the vortices could be also shifted to here and then to here. It doesn't matter how far away, we can just put pause here, 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 and to guide the vortex to the position we want. So this is due to the two-dimensional confinement of the pump. So if we open one direction, for example, the y direction, two pumps are open now, we have the modulation only along x direction, then we can see the vortex is confined along x direction, but can freely moving along y direction. Due to the vortex-vortex interaction, we can see the vortex moving to this direction or this direction. But what is important here is if we only have a single vortex, so without any interaction with other vortices, no opportunity, then these vortices become spatially pinned. So following this idea, so we try to manipulate these vortices in such kind of pump configuration. This is a pump with periodical distribution along ratio direction and also several with finite number of concentric rings. And this pump also creates a similar condensate density in this, for example, here. So in this case, if we put a vortex here, something will happen. So for example, if the vortex with topological charge is minus, then this vortex will propagate or circulate in this orbit in this way. If the vortex carrying a plus topological charge, then this vortex will propagate or circulate clockwise. This is because the so-called Magnus force, for example, if we have infinite rings or the condensates to everywhere, then this vortex also becomes spatially pinned, as we mentioned here. But due to the density gradient, so for example, here the density is maximum and here's density minimum. And the blue arrows mark the density gradient from here to here, the flow of the condensate. And the vortex also carrying the flowing of the condensate. If clockwise rotation with topological charge minus, then we can see the upper position, this region, the condensate flow much faster than here. So here the condensate, the vortex will feel less pressure. The vortex could be forced to propagate towards this arrow, and then due to the confinement of this optical lattice, and this vortex will travel clockwise, and otherwise, on the other hand, the plus charged vortices will circulate towards this direction. This is a circulation of the vortices in our pump configuration. So this kind of circulation could be also realized if we keep the pump fixed, but changing the phase of the vortices. For example, if you have a look at here, the phase is quite ratio independent. If you go from here to here, the phase almost the same in the vortex region. But if we imprint a really strongly strong spiral phase like here, and this, we can see the density also shows strong spiraling curve in the density case. Simultaneously, if we have homogeneous excitation, this vortex won't be spatially pinned. They will move along this circle, have some trajectory in the XY plane, the in-plane motion. If this we increase pump intensity further, we can say this trajectory already deviates from a standard circle, and increase further, we can see the trajectory of the vortex moving is quite complicated, but really funny. Increase further, we can see such kind of trajectory. So to intuitively show this dynamics of the spiraling vortices, we try to use a homogeneous pump P0 starting from 1.5 times threshold, and then increase slowly from here to here to here. We just have a look at how this vortex behaves in the real space. Now we start this video, we can see the circular motion at pump is 1.5. If we increase to 1.9, we can see this very interesting curves trajectory of the vortices of the vortex, and then increase further up to here, we can see the trajectory becomes more complicated and funny. So if we increase still further to some larger pump or stronger pump intensity, for example, to 2.5, then this vortex is strongly pinned. Here you can still see some moving because of the initial velocity, but after some time you can see the vortex becomes spatially pinned. at some position. So this is spiraling vortices. So what is important for the spiraling vortices is the phase distribution. The phase distribution is very hard to be realized if we're starting from some noise, but we could imprint this kind of spiraling phase in our system. So what is also important, normally this kind of vortices appears as a pair. So means they always have interaction. But in this case, you can see there's nothing else, no vortices around this vortex, because our calculation window is quite large. You can see something normally due to the periodical boundary condition. But here we don't have one because the spiraling motion of the vortices will drive the vortices really far away from it. But an exceptional case is if we have two such kind of spiraling vortices, they could survive at the same time and try to circulate. And if you have 3, 4, and even 8, we can see the number of vortices is 8, and the total topological charge is also 8. But for this one, we have spiraling vortex and the spiraling anti-vortex. So you can see the total topological charge then is 0. We could also have a look at this video, how this vortex behaves as time evolves. So we can see the vortex just moving at its own region or that with its own trajectory here, and then they also have the interaction and forming some intensity wall here. So now I would like to introduce how we imprint this spiraling phase, or how we create this spiraling phase. Honestly, this spiraling phase comes from this localized vortices. So which means we create a ring-shaped vortex and then change suddenly the pump to the homogeneous one, then this vortex will automatically jump to this state. So now I would like to introduce the creation and also the switching dynamics of these localized vortices with a ring shape. So generally, this ring-shaped vortices could be created by a ring-shaped pump, because if let's have a look at this equation again. We have a ring-shaped pump. This pump also transfers the ring shape to the reservoir. Then we have a two-dimensional parabolic potential. In this potential, we have the eigenstates, double dipoles, and then we have if the combination can form a vortex. So in this case, what's important if we starting from noise or during the excitation or the in the experiments, there are also fluctuation from the laser or so as excitation manner, then we could create a vortex with clockwise rotation or counter-clockwise rotation. It's not controllable. Of course, if we have imperfection of the sample or the pump, we can create a predefined vortices. But normally, if everything is smooth, we could either create a clockwise rotating vortex or counter-clockwise rotating vortex. If we really would like to use a topological charge to do some application, then the switching between them will become very important. So in the previous study, was the main idea to switch or create a predefined vortices is to break the central symmetry of the system. For example, one can use the chiral lenses to create a specialized vortices, predefined vortices. And we also tried to use an elliptic pump to break the central symmetry of the system. Then we could also create the vortices with specific topological charge. For example, the vortices here and here, they have the same topological charge. Here and here have the same topological charge, and here, these two regions, the vortices have different topological charges. We also thought about use vortex control vortex. For example, if we have some potential channels, we could create vortex, and this vortex will also influence the vortex created here. Or phase-locked vortices, if we have two vortices, they could either have the same topological charge or opposite topological charge, depending on the separation of the vortices. We could also have 3 vortices to create synchronized vortices. This is a vortex control, but if we really would like to use one vortex or during the excitation, we would like to switch these vortices, then this kind of control may not be efficient. Then we come to another idea, how to break the central symmetry of the system. The idea is here, we have the sample, we have ring shape, for the creation of the vortex. And then we have additional pulse to control the reservoir, and then consequently control the dynamics of the condensates trapped in this potential. For example, if we only have the ring-shaped pump here, a vortex is created with topological charge 1, is counterclockwise rotating. Then we put this control beam, at the beginning we consider it CW, control beam just in the ring region of the pump. Then we can create the reservoir in this shape. This potential barrier will break the central symmetry of the system. Then if we have a look at the dynamics of the condensate or the vortices, you can see the oscillation of the orbital angular momentum between 1 and -1. So means we have this oscillating of the vortices clockwise and counterclockwise. They oscillate persistently. If we take a look at several real space image, we can see at this point from +1, then come to here, figure B, we can say it's stopped. We cannot see any current anymore because of the appearance of this barrier. Then this dipole is bounced back to the other direction, to the clockwise direction. Here we have -1. And then when the dipole meet the barrier again, this dipole will bounce back again to the original state. So in this, from this idea, if we control the duration of the pulse, we can easily realize the switching between here and here. For example, we have topological charge is 1 here, counterclockwise rotation. Then we launch the pulse during from here to here, the duration. Then we can say the dipole, the vortex is stopped and then bounced back. Before bounced back again, we can remove this control pulse. Then we can see the vortex with the opposite topological charge is formed here by control the duration of the pulse. Here is our collection, how this switching depends on the control pulse. For example, we have the same intensity of the pulse. We have switching off, on, which means due to the periodicity, these switching dynamics appear alternatively, off, on. So we also found the switching dynamics or the oscillation also depends on the intensity of the pulse. For example, if the pulse has a fixed duration, as the pulse intensity is smaller, we can see no switching. Increase, we can see switching, and then no switching again. This also appear alternatively for the switching dynamics. Then we bring the results to our colleagues in Dortmund within this cooperation. So in the previous case, people measure the phase of the vortex by using the microsome interferometer. So for example, do the interference, if we can see here the fork shape, then we can confirm here's a vortex. If another direction, then the topological charge is opposite. In our work, our colleagues do the phase measurement by OEM sorting, which means for the details, one can goes to these two papers for the details, the experimental details. The basic idea is to open this vortex because different vortex topological charge have different size for the vortices. So if we open the vortex, do the projection on the OEM region, then we can say, for example, this one, do the projection, we can say the main peak stay at topological charge, quantized OEM is 1. And then if we have the other rotation of the vortex, then we can see the occupation of the peak will stay here at this point, -1. This is a basic idea how they do the OEM sorting to measure the phase of the vortex in experiments. And here is the result. For example, at the beginning, the pulse is launched at T0. Here is no pulse excited, but only ring-shaped pump. We can say at the beginning, we have topological charge is 1. Here is also 1, here also 1. But due to the injection of the pulse, if the pulse intensity is 1 milliwatt, we can see that no switching happens. Here we can see something, but this is a fluctuation from the pulse. For a weaker pulse, we can see there's no switching happens. And for the stronger pulse, we can see the topological charge already from 1 jump to the -1. So we can see the switching already. And if we increase further of the pulse intensity, we can see the switching happens and then jump back to the original state. which agrees well with our theoretical prediction following this line: no switching, switching on, and switching off. So up to here, I already introduced the vortices, the control of the vortices, and but mainly on the fundamental mode, which means we only have topological charge, or the winding number is 1. Topological charge is -1 or +1. So what would be important if we could have higher order vortices? For example, topological charge 2 and topological charge is 3. So normally in our case, if we increase the radius of the pump, increase the radius of the ring, then we could easily create a topological charge is 2 and 3, depends on the eigenmodes of the parabolic potential. But is interesting in our system, we have this saturation term in the equation, or the scattering term. Physically, we call it scattering term, to couple back to the original equation. And this term, we can see the density of the condensate will also strongly reshape the density of the reservoir. So by using this one, we could also realize the higher order vortices under the same pump excitation. So the idea is this. So first, I would like to say for different topological charges, the vortices have different radius. If we have look at topological charge 1, the radius is this size. Topological charge 2 becomes to here, and the topological charge 3 is much bigger than the topological charge 1. So in this case, different solution will reshape the reservoir. For example, if we don't have this shape, this term, then the potential, optically induced potential, will follow this dashed line, this one. Due to the reshapement of 3 different solutions, we can see the red one is modulated by this solution, green one is modulated by this solution, and blue one is modulated by this solution. So we can see they are not completely different, but in the core region, they are different. So this difference will give us an opportunity to see the vortex multi-stability, which means we have the same pump. Due to the modulation of the condensate on the reservoir, then we could have stable vortex with topological charge 1, 2, and 3. So we call it vortex multi-stability in this case. So I also would like to mention a bit, because normally the topological charge 2 or even 3, I mean, as topological charge increase, normally they are unstable or they repel each other. The core region will be split. So it's not that stable. But in our work, our colleagues measured something already to say this topological charge 2 is quite promising. I mean, it depends on the system's parameter. In some case, it could be realizable in the near future. So now, up to here, we talked about the fundamental vortex and also higher order vortex. We never talk about the spin dynamics. So if as we know that we consider the spin dynamics of polaritons, we could also create such kind of interesting half quantum vortices. For example, if we have a linearly polarized pump, of course, sometimes also could be a circularly polarized pump, we can create some condensate in the sigma plus component and some condensate in the sigma minus component. And in these two components, you can see the distribution of the condensate actually is not that the same, it's a little bit different. If you have a target on this region here, this density minimum, but in the sigma minus component is not, you can see the density. So in this case, if we measure the phase, we can see the phase singularity in the middle. So which means here's a vortex, but in the sigma minus component, we have nothing, no phase singularity. The phase is flat, so it's no vortex here. So if we calculate the topological charge in general, then it's a quantum number, it's a half. It's not an integer number anymore. So in our case, we also try to create the half quantum vortices, but with localized shape, with a ring shape. We still using this configuration, a microcavity excited by the ring shape pump, but then we use linearly polarized pump. And this linearly polarized pump will simultaneously excite the polaritons in both sigma plus and sigma minus component. But what's interesting is we could create a vortex in the sigma plus component, but a non-vortex state or fundamental mode in the sigma plus component. So what is quite interesting, because normally if we have a TTM splitting or the spin optic interaction in the system, we create a vortex in the sigma plus component and generally a minus a vortex with opposite topological charge in the other component, but they have the same energy normally. But in our case, we can see sigma plus component, we have vortex, the energy is here, the frequency, but for the fundamental mode, it has a lower energy. So which means the half vortices have a lower energy than the standard spin vortices or the full vortices in two components. The other very interesting dynamics for these half vortices is polarization in the core region of the vortices. For example, this vortex, we have a topological charge here, then no density in the middle, but fundamental mode, we can see a clear intensity peak in the middle. So if we calculate the polarization in the middle of the condensate in total, then we can have either the circularly polarized condensate or or the other one, right-hand or left-hand circularly polarized condensate. In this case, if if we would like to measure the half vortices, then we don't need the phase information anymore. We just measure the intensity in the middle, in the core region. Is circularly left-hand circularly polarized or right-hand circularly polarized? Then we can confirm here's the vortex, half vortex or not. So this is for the vortex in the plus component. The vortex could be also in the minus component. For example, this one, then we can see these two polarization are opposite. Yeah. Also the other one, if I have a plus charged vortex in the plus component, they have the same polarization in this configuration. So now we also would like to see if we could switch this polarization of the condensate between these two half vortices state. For example, if we imprint a coherent vortex in the minus component, coherently imprint a vortex, this vortex will be imprinted in the condensates, of course, because of the incoherent pump, and then simultaneously due to the TTM splitting and the cross interaction, this vortex core will drive this or repel this vortex core out of this region, this vortex. Then we can realize the switching of the half vortices or topological charge transferred from the plus component to the minus component. Then we realize the switching of these two states by the reverse polarization of the condensates in the middle of the vortex core. So this is switching from -1, 0 to 0, -1 corresponds to this one. We could also realize the switching here and switching here as well as the switching here. So this is a fundamental, or we call it fundamental half quantum vortices. Later, we tried to extend the pump radius, increase the pump radius. We could also create a much complicated one. So here is the fundamental state. We go one step further, we can see these half vortices, half vortex region. And if we go further, as the pump radius increase, we can see the full vortices, or the spin vortices. And if even we increase further, we could see topological charge 2 in one component and 0 in the other component, and so on. The different combinations depends on the radius of the pump. So now up to here, I already finished all the important part, and I would like to conclude a bit of this talk. In this talk, I introduced two kinds of vortices. One is non-localized vortices. Then we can realize spatial control manipulation, or due to the Magnus force, we can realize circulating of the vortices or completed phase information. We could also see the spiraling vortices. And for the localized vortices, we could realize the switching of topological charge by single vortex switching, or vortex phase-locked vortices to realize the switching of the topological charge, as well as topological charge switching between different spin components. So at last, I would also like to thank our funding from German Research Foundation, and also the National Science Foundation of China, and also our Center for Optoelectronics and Photonics. I also would like to briefly mention that we have a PhD position available at the moment. If you have any students who are interested, there may be an opportunity. So at last, I would like to thank you very much for your attention.
Thank you very much, Xuekai. Very a lot of results, very interesting talk. I'm sure there will be many questions because, as you know, our groups are working on the experimental realization of
I know, yeah.
States. So I will try to navigate the discussion here. So if you have a question, raise your hand. If you do not know how, just send me a message on the chat. Okay. And I see Tamsin. Please go ahead.
Hi, thank you for a very nice talk. Could I ask a question about initially about slide 16? I think it was. Sorry, it's quite a way back.
It's okay, no problem. 16. Yeah.
Yeah, so I have a question about the central top row. So most of you have 3 small vortices appearing on the maximal of the density, and then you have a very large point at around 15 or something that's on a minima. Why is one of them so much bigger than the others?
Yeah, I think this depends on the confinement of the vortex. Normally, I didn't mention here. So the vortex size is really depends on the background intensity or background density of the condensate. So as the condensate density increase, the vortex is strongly pushed, then have a smaller shape. So if you have a look at the density here, it's around 120, and here is roughly 80 or so. Then this size is much larger than this one.
Okay. It's just that surely if it's got the higher density at the sides, it would confine it more.
If you remember this video here, you can see as pump intensity is 1.5, this core is quite large. If we go, for example, to 2.5, this core is quite small.
My next question, if it's okay to ask a few, was on slide 23. That's okay.
Yeah.
Yes. So on the top graph on the right, I had to think about the side of the slide. You start off at 1, and then you go into this oscillation, but only in the first oscillation are you at 1 and -1. After that, you're at 0.8 and it's reducing. So how do you determine whether it's still a vortex of charge 1 when the peak doesn't reach charge equal 1?
Yeah, this would be, we have to simulate, first we have to plot this this figure here. We have to check where is the +1, where is the -1, and then after some time. So normally we just choose some region here. We have 1 pulse, then to here, for example, we just measure 100 picosecond, and we just set the pulse around 100 picosecond, and then we can see the switching or not. And then we can wait for a longer time. For example, the pulse reach 200 picosecond here, then we can see the switching back again. Normally we don't come to here. I just pick up several profiles, looks perfect. If here maybe not that perfect, we cannot see clearly the dipole, but here is much clearer.
Right. The other, on this one, I think I missed it. How exactly did you prepare the state with charge m equal 1? Because you said part of the reason with this was vortex control, and so part of the reason of this work was for vortex control, but you can clearly prepare the state in charge m equal 1.
Yeah, normally this charge 1, we just take an example here. Normally during the excitation, it could be a plus or could be a minus. This really depends. And if we have a minus, we could, so for example, if you check here, this results, we could always analyze what's this vortex without any pause before. But due to the imperfection of the sample, we always, in experiments, we always have a disorder of fluctuation. Once the vortex in the plus with topological charge plus, then the second time you set the potential, the sample at the same position, use the same pump, probably have the same vortex. And so we can confirm by this way. Otherwise, if you, for example, you have a look at here, then you can say, okay, it's +1. If you want a -1, then put some pause here. If you just want +1, then you don't need
So sample disorder can dictate whether in these cases you were relying on sample disorder to dictate it to always be +1 or always -1. It wasn't stochastically flipping it.
At least in our colleagues' measurements, if some position is +1, then probably always +1 after some time to re-excite the sample.
Okay, thank you very much. I'll let others, I'll ask questions at the end of this time. Thank you.
Okay, so let's move on to Sergey. Sergey.
Thank you very much for interesting talk. My question is about slide number 15. So here, I think the next 16, and yeah, the next slide. Yeah. So here, what was the minimum periodicity of the fringes so that you could observe vortices in two edges and lines? Because if you decrease the width, yeah, at some point, because of healing lengths, probably you will not be able to see vortices, but within one line, you should get 1D array of vortices. Did you observe such?
Yeah, actually, so what I didn't mention in this case is, so normally if you compare this pump and lattice, the pump maximum, for example, we consider the maximum 0 and 0, this point. So, no, this is minimum. So the pump minimum 0, 0 point, if we check the 0, 0 point here, then this point is the condensate maximum. So in some case, which means we have the condensate, at the condensate minimum, we can create a localized vortices, is for sure because of the confinement from the surrounding condensate. But this pump will behave like a reservoir. This reservoir also provide a confinement, like the optical, no optical, the excitonical confinement also. So in this case, some vortices could also be confined in this condensate maximum, a minimum. So that's why in our case, we always have two kinds of vortices, because the maximum of the condensate and the maximum of the reservoir, they are different, they are shifted.
Okay, can you say what was the typical healing length if this term is applied here in such simulation?
Yeah, good question. This healing length is really depends on the background density or the reservoir density. Here, we do have some calculation in this paper, and this healing length is also depends on the background density of the condensate. Maybe we can check this paper out.
Thank you very much.
Thank you.
Okay, let's move on to Kirill.
I have a question according to the slide number 26.
I'm so sorry, there's not so clear a signal for me. I don't know for the others.
Kirill, we cannot hear you.
Could you hear me now?
Yeah, yeah,
yes.
Much clear.
First of all, thank you for your presentation. It was really nice. My question is according to the slide number 26.
Mm-hmm. Ah, 26, 24. Yeah.
Yeah. Is it possible to switch back the direction of the vortex when the control pulse arrives to the sample? So let's say in several hundreds of picosecond, you send the same control beam, and will the vortex flips to initial charge?
You mean this flipper? I can see the mouse. So if I understand correctly, so here we have as pulse intensity increase further, we can see the flip of the topological charge and then flip back. Like I mentioned, if in the sample you have the same sample geometry also, or the same excitation method, we always have +1 charged vortex formed. So in this case, it doesn't matter. So we have switched this figure 3. If you cannot see the mouse, you can see the switching here and then back to the original state. Yeah, this is for sure. But here, I would like to explain a little bit here. We have the switching happens, but due to the sample disorder or so, after some longer time, this one will also, for example, maybe here up to here, after a really long time, I forgot the time scale, but quite after some time we measured, then this vortex also spontaneously switch back to the original state. But it takes quite a long time. How long this duration? I cannot talk. I think we discussed something in the paper. Maybe one could check the time duration, how fast it is relaxed to the original state.
Okay, thank you. And one more question, according to the next slide.
This one or the previous one?
So yes, you show the vortices of
Mm-hmm.
higher charges. What is the reason? Maybe I didn't get from this slide.
Yeah. The
What
reason
is the reason why the charges higher than 1 are stable and they are not decomposed to the simple.
Yeah. The reason is this. I switch to the later point. So the reason is this term. So this term is the modulation. This term will modulate the distribution of the reservoir. And if this term is significant compared to gamma R. So in this case, if we don't have this case, we have the potential always fixed because the pump is fixed. So because of this part, one can also think about this is similar to the hole burning effect in laser physics. If this one burning a hole, and this hole position will be different depending on the topological charge of the vortices. For example, topological charge 1 is burning the core region very close to the core region of the pump. And then the topological charge 3 will burn, the blue line will burn mainly this part. So different reshapement will give us different reservoir potential, even in the same pump. So this reshapement of this solution on the reservoir will give us 3 different stable states. And actually, for these 3 different stable states, even we have the same pump, but the reservoir is already changed. This is the main idea because
okay, thank you.
Yeah.
Okay, Nina.
Yeah, hi, thanks for the talk, very interesting. My question is about this last part, about imprinted vortices and the switching, maybe starting from this slide and further. So the question is, what is the role of nonlinearity in the Gross-Pitayevsky? Because these vortices, they are optically imprinted, so their size is fixed by the pump, basically. So would all that you talked about stay the same if we remove the interaction completely, or it plays a role, and how robust are all these effects to interaction? Thank you.
Yeah, so normally, you mean this, so here the 3 vortices, I mean, it's stable just independently, not they stable in the same pump simultaneously at the same time. So, for example, this first one is stable, but then we cannot say this 2. So there won't have any interaction between these 2, the nonlinearity. So if this is stable, then this system only have this solution. So if this is stable, we just, for example, take the initial condition of topological charge 2. So for this one, we take the initial condition like topological charge 1, imprint this one, we only create this solution. Then we recalculate. Then we use topological charge 2 as the initial condition, then this is stable. Then this is stable for topological charge 3. That's why there's no interaction between these 3 for this due to the nonlinearity. But for each one, single one, due to the nonlinearity, the the vortex also becomes unstable when the topological charge increase. Even for this one, the stable region is less than this one, is much less than this one about the stable region due to nonlinearity.
Okay, I meant not interaction between the vortices. I meant interaction between particles, which enters as a nonlinear term in the Gross-Pitayevsky. So I can reformulate maybe. So if I replace the Gross-Pitayevsky equation with the Schrödinger equation, in which you again imprint as initial condition whatever charge you want, probably everything will stay the same, correct?
I would say yes, because we can consider this case like we just slightly increase the pump intensity above the threshold, just slightly 1.1 or 1.01. Then we can see three states are stable for sure.
Okay.
This is not like in nonlinear optics, because in nonlinear optics we have this vortex initially imprint, but in our case we have the confinement of the pump all the time. Then this vortex cannot be easily destroyed or go propagate to some bigger shape also.
And if you increase interaction in your simulation, then what will happen? I mean, particle-particle interaction.
I would say the vortex would be, I mean, at least at one point, the blue shift is significant. Sometimes if you have spectrum here, this energy may move out of the potential already, getting unstable. And on the other hand, the interaction, I would say, will break the vortices.
I would just say that maybe they should shrink, because the healing length will be more defined if you increase the density or interaction constant. Yeah, but thank you.
Yeah, maybe. Yeah, you're welcome.
Okay, Stella.
Hi, thanks for the great talk. Can you go back to slide 26, please?
Yep.
Yes. So here, when you have the 20 milliwatt pulse, before the pulse is introduced, your condensate is mainly in the +1 charge. But after the pulse, to me, it looks like there's an equal contribution of +1 and -1. So
you mean here or here?
Yeah, after the pulse, at around 1,000 picoseconds.
Here.
To me, this looks like an equal contribution of the +1 and -1 charge.
Yeah, actually, to be honest, here, if you have look at here, it's also quite close, because of the sample. We do measure the sample is, I didn't show the original vortex here. This original vortex is quite not that perfect. So always like a dipole.
Yeah,
so, but this dipole,
dipole mode condensate from a complete track.
Yeah, but one can clearly say there is something between this dipole in the big, for example, the dipole line along y direction. You can see the density along x direction, which means if you have a plus and a minus, if they are equal to each other, then we have a dipole. But in our case, the plus indeed is larger than this minus component. That's why we do see the -1 because of the dipole similar shape.
Yeah. Okay. So I was going to ask, do you use any specific criteria to say whether or not your condensate is in the dipole mode or in a vortex state? Like, do you say whether or not you can see the dark core to this in the condensate density to say there is a vortex? Like, specific definition of whether you're in a vortex.
Yeah, actually, the density is quite strange, quite hard to judge is vortex or not, because if we have, for example, the disorder could also, if disorder just distributed in a dipole shape, then this condensate could also be trapped into different disorders. Then it could also a dipole shape, then we don't know. If we measure this one, we do have some similar data. Then we measure this one, we will have some central peak. The peak will stay here, and the topological charge is 0. If it's dipole mode, then we can say 2 equal peaks at 1 and -1.
Okay. Okay. Thanks.
Welcome.
Okay, Kelaris, next.
Hello, hi. Thanks for the very nice talk. I'm not an expert in the field, but I was wondering, you mentioned that when you create these vortices, right, whether they are +1 or -1 depends on, it's stochastic, right? And it might depend on the effects of your sample. My question is it possible to engineer these defects so that you can define the charge, whether it is plus or -1?
Engineer, you mean the sample or the pump?
Both.
Yeah,
you said it depends on the sample mostly, right?
Yeah. So here,
is it possible to do that?
Yeah, here is a example. For example, we engineer the pump. You can see this is a pump shape, the spores. This is a pump. It's not a ring anymore. It's a ring shaped, but it's with different spores, pump spores. If this is if they are symmetrical, they are non-chiral lenses, non-chiral pump. Yeah, so the same, and then create a vortex could be depends on the sample plus or minus. Sometimes if we calculate, could plus or minus. But if we have this chiral distribution of the pump, we could say this predefined vortex could be created. For example, this one. I think for the pillars, we could also do the same thing. If we have some defect in the pillar, make the pillar chiral also, I think the vortex could predefined vortex could be created for sure. Because
okay,
even yeah, sorry, I didn't hear. And so I mean, for example, even we don't do anything in the sample, we always, due to the samples disorder, we still say the predefined vortices. This is depends on the disorder distribution. This is for sure could be realized.
Okay, thank you very much.
Welcome.
Okay, so we have reached 1 hour. I have one more question because before I go back to Tamsin, which has to do with the case where you start including the spinel component of the condensates into consideration, slide 29. And there, where you pump linearly, which means that you pump an equal spin up and spin down exit on reservoir, your simulation, your numerics result to a splitting between sigma plus and sigma minus. So the first question is, how does this depend on the strength of the spin up, spin down polarity interaction with respect to the polarity interaction between the same spins? So you have added an extra term that you didn't talk about, yes? You have added a term which is the spin up, spin down interaction in your GPE, correct?
Yeah. Actually, in our paper, we do discuss. We did discuss this cross interaction in our case. As I can say, this formation of this half vortex, it is not that important to related to the cross interaction, but the switching. So, for example, here and here, the switching is important. So, for the switching, if we have the cross interaction, we imprint the topological charge here. Then, due to the cross interaction, this vortex will have interaction with this one. Then we can realize the switching. And for the formation, even we don't have cross interaction, we could still say this half localized vortices.
So let me understand, every time you run your experiment, in one case you will have a half vortex in one component, and if you run the simulation 1,000 times, it is completely stochastic what is at a higher energy and what is at a lower energy state.
Normally, we do for confirming the half vortices. Yes, we do the simulation like at the beginning. We give vortex in one component and non-vortex in the other. But sometimes we also use noise. But use noise, these two will depend. Topological charge could be in this component or this component, and the topological charge could be also plus or minus. But for doing to collect the information here, we always use define the initial condition. This could also use noise initial condition could be used. I mean, in experiments, if you use just a linearly polarized pump, I think circularly polarized pump could be also okay due to the fluctuation also or the relaxation. That's why even have noise, we could also see this vortices, for example, like this paper. Always have noise, then we could also realize this. Because the vortex is formed automatically during the excitation. But with noise, there will be some problem because there could also realize the vortex and the vortex, different possibilities.
Okay, thank you. So last question from Tamsin Cookson.
Yep, sorry, there was just two small ones. This image in the top left, where you show how you set up your state. you show a really wide ring mode and then your condensate sat on top of that. Can I just clarify whether your condensate is trapped within your pump or is on top of your pump?
Generally, it's trapped. Of course, there will be some particle goes through the barrier because if the barrier is something in the quantum mechanics, they could also have some tunneling to the outside of the.
I thought so. I was just questioning because I've looked at this image now quite often for like an hour, and the condensate looks like it's sat on top of the pump, and I wanted to clarify. The other question I had was on, I think it was 27. It was about the higher topological charge. Yeah, here. So you've obviously changed the radius of your ring modes to get these different ones. When you were doing this, was this like a step function where you'd have m equal 1, m equal 2, m equal 3, or at the point where you jump from 1 to 2, is there some instability? Do you ever get two vortices of m equal 1 together before they join to an m equal 2, or how dynamically does that?
Yeah, during the excitation, if we increase pump intensity, it's quite different because there will be some oscillation anyway because of the two modes will appear sometimes at the same time. There will be some beating or some interaction. Then we'll slowly jump to the topological chapter 2. I don't think it would be a exactly perfect step, but there will be some jump. And in the middle, the oscillation may really disgusting. I mean, to recognize this. Topological chapter 1 or 2 because this will be a lot of spores, not a ring shape anymore with the interaction.
Okay, thank you very much.
Okay, last round of questions, Sergey.
I have quite general question. What are the perspectives of investigations of vortex lattices, except some information processing, and can be used as a test bed for some models?
I didn't quite follow.
So usually in the literature, people say that vortices can be used for information processing and storage. And the question is, what are, in your opinion, the perspectives of further investigations in these directions? Can be the vortices used as some test bed for some models?
Actually, I would say why we say this would be important for information processing or storage because of this binary information. Normally, if we consider the continuous, for example, standard Gaussian pulse, we have switch on and off depending on the density or the intensity of the pulse. So we can not really, if we really close to the transition point, switch on and off, then sometimes it's not clear. But for the vortices, we have a quantized topological charge. We could either have 1 or -1. We could not have any middle state. That's why it would be promising for the binary information. If, of course, information processing, we need some data storage. We need the binary one. For example, here if we consider the plus and the minus, it corresponds to 1 or 0. This binary information, then we can apply to this one. About how promising this one or some model, I'm not really an expert in this field about this information processing also, but there would be an opportunity.
Thank you.
Okay, and the very last question is coming from Kirill Sitnik again.
My question will be about, again, vortices higher than the charge 1. Could this be used as the criterion of condition of polariton condensate? So let's say if we can observe the vortices higher than charge 1, does it mean that we not in the superfluidity condition? Because for atomic condensate, it was shown, actually you showed this on one of the first slides of your presentation, that the charges decompose to the simpler state.
This one, huh? You mean the optical?
No, there was some 4 images, black and white, with 1, 2, and yeah, this one.
Okay, yeah. I would say this is just an example. I would like to emphasize why this vortex is important in general in condensates. because it's not only investigating optics, it's also have been done. I mean, this is not the only paper, a lot of papers in condensates, and then yeah, we also in Polariton condensates, like a kind of advantage of these vortices why people are interested in.
Yes, but my question is, can we use the possibility to generate vortices higher than one charge?
In this case?
Yes. Does it mean that we're not in the superfluid state of the condensate if we see vortices higher than charge 1 or -1?
You mean in our system, we also use laser to steer the condensate?
I mean, in the experiment which was shown on the 27th slide, when you show possibility to generate states with charge 1, 2, and 3.
Ah, okay, yeah, here.
Thank you.
Yeah, use the laser, I'm not sure, but it could be possible to create these vortices as well. And this vortex, of course, we like what we see in the condensate. We also split this vortex core. That's why I'm not sure if we're still using the laser to steer to create this higher order vortices. But it may possible. The question is, in our system is different. I'm not really familiar with excitation. If we are possible to steer the laser very fast in our case, because you know the gigahertz angular momentum, for example, here. Yeah, so I don't know this frequency could be that fast, but it would be possible if. Yeah.
Okay, thank you.
Okay, well, with that, I think we should close. Xuekai, thank you very much for very interesting talk and answering all these questions. I would like also to thank all the people who have joined us today. And yeah, we will see you possibly all at our next seminar. And Xuekai, thank you again very much for coming along today.
Yeah, thank you, everybody. Bye.